Okay, so we're still doing optimization, right? And as I mentioned in the last video, right, most of those were fairly routine. The last one got a little bit tricky. And then this one, I think, is probably sort of about the same. Yeah, it's a similar type problem. It's a very geometric problem, right? So you have to know a little bit about hemispheres and cylinders and things like that, right? So so the question says the following, right? So this is our first example. A solid is formed by adjoining two hemispheres to the ends of a right circular cylinder. The total volume of this solid is 14 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. Okay, so like I say, it's this comes directly from the homework. In fact, I would highly suggest you try this on your own, right? See if you can come up with the answer before you watch me do it, right? So whether this is a homework problem or not, you should try this on your own. Okay. Right. So yeah, first things first, and I don't think it's in but maybe it's in WebAssign, but I don't know if it's in the book. I don't see a picture here. So let's read this carefully. We have a solid formed by adjoining two hemispheres to the ends of a right circular cylinder. Okay, so here's my right circular cylinder. Let me try that again. And see if I can make that as straight as possible. I have difficulty making straight lines here. Okay. Let me see if I can do it this way. Oh, that's even worse. I don't know. How did I get the first one to be so straight? All right, that's as good as I'm going to get, right? That's a cylinder, right? It's a cylinder, but it's only part of the solid, right? What are we doing? We're adjoining or attaching two hemispheres to the ends. So if this is the top end, we'll just attach a hemisphere. That's half of a sphere, right? Does that look like a sphere? There we go, right? And then the same thing for the bottom end. So we get this shape here. And, it doesn't really matter which way you orient it. If you drew a cylinder lengthwise like this, I'll try to make it look like this. And that's not quite a right circular cylinder, but close enough. Right, then your hemispheres would look like this. Right? So it looks, like a capsule, right? Like a capsule of sorts, or a pill of some kind, right? So that's the picture. Again, the one on top, the vertical one, looks a little bit neater, so I'm going to go with that one. But you could have drawn it either way. And what do we know about this solid here? Its volume. We know its volume. Ooh, that's kind of dark, right? Is 14 cubic centimeters. So that's the volume. So what do we want to do? We want to find the radius of the cylinder. Okay, so let's draw the radius. This is my lowercase r. Now notice in this case, the radius of the cylinder matches the radius of the hemisphere, right? This is the same radius here, right? So the radius of the hemisphere is the same as the radius of the cylinder. What else do we need? We need the height of the cylinder. So we'll call that lowercase h. Right? So what do we want to do? We want to find the radius. We want to find r that produces the minimum surface area, right? So they're very clear about it. We are minimizing surface area. Okay. We're finding the smallest surface area possible, given that the volume has to be this amount here. So we can't just make a smaller cylinder with a top and bottom here. right? Because then that's decreasing the volume. So obviously that would decrease the surface area as well, but we can't change the volume, right? So what can we do? Well, we can make it a thinner cylinder, but a taller one. So, see, I just can't draw straight lines. I'm sorry. Pretend those are straight lines, right? And then a very tiny dome at the top and bottom, right? So is that, I don't know, is that a bigger surface area, smaller surface area? It's not very clear, right? Right. The other possibility is to make a very, I'll do it down here, a very short cylinder, but a very big dome on the top and bottom, right? So is that, again, without changing the volume now, so maybe I made that a little too big. So maybe I'll make it a little bit wider. Yep. And say that's the same volume, right? Now, which surface area is bigger? The one on the bottom or the one on the top? Right. I don't know. That's the question, right? So what should R be? What should the radius be so that the surface area is minimized? Okay. Well, how do we find the surface area, right? So surface area, right, which I'll just call A for area, right? Well, what do we have? We have the dome, the hemispheres, and in fact there's two hemispheres, right? So if we detach these and then connected them, there's the one on the top, there's the one on the bottom, what do we get? We get a sphere. Okay. So what's the surface area of that sphere? I hope you know it, or look it up, right? It's just 4 pi r squared. Right. So this is for the spherical part. Okay. Plus, we have what's in between. What's in between is just the cylinder, right? Just the cylinder without the sphere on top and bottom, right? We're cutting those off now. So what's the surface area of the cylinder? Well, here's the cylinder. I think I went a little outside the bounds here. Erase those. Yeah. What is the surface area? Again, that's something you can look up as well. Think of unfolding this. If you unfold it, you have just a rectangle where the height is still h, but now the base is just taking a circle and expanding it out. What's the circumference of a circle? 2 pi r. So what's the area of this rectangle? It's 2 pi r times h. Okay. So that's for the cylindrical parts. Cylinder, right? Now, when you look up the formula for the area of a cylinder, you might get this as well, the 2 pi r squared. Where did that go? Or what is that? What is the 2 pi r squared? Well, pi r squared is the area of a circle. Where do we have a circle? Right up here, the top of the cylinder, right? And the bottom of the cylinder. So if you want to include the top and bottom of the cylinder, the closed cylinder, then you better include the 2 pi r squared. But in this problem, we're not including the top and bottom. How do I know that? How do I know that we're not including the top and bottom? Because the top of the cylinder, right, got replaced with the sphere, or the hemisphere, the dome, right? So no, we only want the outer surface. We don't want anything inside the dome, right, or the inside of the cylinder. So no, we're not counting this, right? It's just a complete solid. We want the area of the sphere, the top and the bottom, and then the side of the cylinder without the top and bottom disk here. Okay. So I think this is it. This is the total surface area. And I'll just write that in yellow now. Total surface area of the object that we want. 4 pi r squared for the top and bottom of the sphere. Well, each one is 2 pi r squared, right? But there's 2 of them. So when you double it, you get the total area of the top and the bottom. That's 4 pi r squared. Oh, maybe I'll leave that, right? And then the cylindrical part is 2 pi rh. And there we go. Right? So this is what we want to minimize in the end. And how do we minimize it? Well, right, take the derivative, set it equal to 0. Find the critical numbers. But before we can do that, we have to recognize that this depends on, again, pi is just a number, but it depends on the radius and it depends on the height. We have a function of 2 variables. So how do you take a function? How do you take the derivative of a function of 2 variables? Okay, so that's a Calc 3 problem, but we're not going to do that here. So, I mean, if you know how to do it, if you know partial derivatives or total derivatives, you know, go right ahead. But the point is we don't need it in this problem. We don't have to know anything, any multivariable calculus here. We simply have to find a secondary equation, right? So again, this is our primary equation. Now we need a secondary equation, which is a relationship between r and h. So what's the relationship between r and h? Yep, that's a tricky thing, right? It's not given in the problem by any means. We have to determine that. We have to find the secondary equation. We have to find how r and h are related. Okay, what's the only thing we have not used yet in the problem? How about this? Nowhere did we use the fact that the volume was 14 cubic centimeters. So that looks like a good place to start, right? What is the volume of this object? Well, let's see. We have a cylinder. The volume of a cylinder, which we did in the previous video, is pi r squared times h. And then we have a solid sphere, right? A ball. What's the volume of a ball of radius r? 4/3 pi r cubed. Okay, so again, this is the cylinder part plus the spherical part. And yes, there's 2 spheres. There's the top and bottom, but when you combine them, you get a single sphere. And then that's the volume of that sphere, right? So there we go. This is the volume of the object, pi r squared. Well, I'm not going to copy it down. We already have it here. And what do we know about that volume? It's 14 cubic centimeters. So this is all equal to 14. You know, cubic, right? So our units here are centimeters. So volume is cubic centimeters. The area, of course, will be square centimeters. Okay. Okay, so there's our secondary equation, right? And this is an equation. And so what do we have to do? Well, we have to solve for either r or h. And then whatever we solve for, we'll plug that into the primary equation up here. The yellow one on the, yeah, this is our primary equation, right? Yes, yeah, it's the same one as this. Okay, so now the trick is to figure out, oops, sorry, I'm using the wrong color here. Let me just erase all that. So now the trick is, what do we want to solve for? Do we want to solve for r or h? Right, and I hope the answer is obvious. So let me just copy down the equation here. This is a relationship between r and h, right? And not a simple one. It's a complicated relationship, right? It's a complicated equation. But it does, right? If I tell you that r is 1, you can find h. If I tell you that h is 2, you can find r, and vice versa, right? So this is a cubic equation, right? It's not even quadratic. It's a cubic equation in R. So do you know how to solve a cubic equation for R? Not easily, right? Because there's no quadratic formula. So solving for R here, solving for R. I would have a very hard time doing that myself. I would probably have to resort to a computer to be able to figure out how to solve for R in terms of H. So I think our goal here is to solve for H. Why? Because there's only H to the first power, right? There's only this one H here. That should not be hard to solve for. Solving for R involves taking, square roots or cube roots, or both in this case. Very tricky to solve for R. So, yeah, just whatever you think is easiest, solve for that, right? Solve for H. So, how do we do that? Well, we have to subtract everything that doesn't have an H in it. The 4 pi r cubed gets subtracted from both sides, right? And then that gives us, let's see, pi r squared h equals 14 minus 4/3 pi r cubed. And if we want to solve for h, we might want to divide by pi. And while we're at it, the r squared as well. So oops, these things just cancel. And there's our equation for h. I'll just write it down here. H is going to be 14 minus 4/3 pi r cubed, all divided by pi r squared. And maybe I'll just copy it down over here. Oops. Make that big enough. 4/3 pi r cubed all over pi r squared. That's supposed to be a pi, right? All right, close enough. All right, so what do we do with that h? Well, everywhere we see an h up here in the primary equation, we'll just plug that in up here, right? Maybe before we do that, might I suggest, can we simplify this expression a little bit, right? We have a common denominator, so I'm going to split up the two fractions as two separate fractions. You don't have to, but I think that probably makes the most sense here. Right. And after all, on the right side, we can cancel the pi's. We can also cancel 2 of the r's. And when we do that, we get, let's see, 14 over pi, how about r to the negative 2, minus 4/3 times r to the positive 1. Okay? Yeah, I think that might look better, right, when we plug that in for h up here. Okay, so let's do that next. So let me just copy this down because, again, we've got to do this. 2 pi r h, yep. And now we know what h is, right? It's all of this mess over here on the right, the stuff in green that's in the box here, right? So right, there's no h here, so we can leave that as pi r squared, plus 2 times pi times r times h. So now in parentheses, this will be our h, but now in terms of r. See that? Right. And still, before we take the derivative, I would strongly suggest distributing the 2 pi r here. Again, you don't have to. If you'd rather use the product rule, go right ahead. But I think we might be able to avoid the product rule. So let's see, 2 pi r times 14 is 28 pi r. Oh, sorry, r to the, oh boy. So 2 times 14 is 28 times pi, and then r times r to the negative 2 is r to the negative 1 divided by pi. Okay, so now we get another pi that cancels here. And then for the second term, we're going to get minus, let's see, 4 times 2 pi r is 8 pi r times another r for r squared, all divided by 3. Is that right? So 2 pi times 4 is 8 pi, times r is r squared, divided by 3. Yep, that's it. So let's see what we get. We get 4 pi r squared plus 28 r to the negative 1 minus 8 pi over 3 r squared. Okay, so this is still my primary equation, right? This is the surface area. Yep, surface area. We want to minimize this, right? So the area as a function of just r by itself is this thing here. And, you know, well, you don't have to, but I think this, look, we have two like terms here, r squared and r squared. So all we're going to do is take the 4 pi and subtract 8 pi over 3. So can we do that? So 4 pi over 1 minus 8 pi over 3, all times r squared, and then plus 28 times r to the negative 1. Again, maybe not necessary, but, you know, look, common denominator here is 3. So we get 12 pi over 3 minus 8 pi over 3 is 4 pi over 3 times r squared plus 28 times r to the negative 1. So I don't know about you, but this looks a little bit simpler than what I have up here. There's only 2 terms instead of 3 terms, you know, because 2 of the terms were like terms. They have the same exponent, right? All right, well, that I think is about as simple as it gets, right? So our final primary equation, primary function now, is a function of just r, is this. And I'll write it as 1 over r instead of r to the negative 1, either way. So maybe this is a good time to pause because we did a lot of work here. So let's back up and just figure out where are we at here, right? The question was to find the radius that produces the minimum surface area. And we had our surface area as a function of r and h. And so in order to eliminate h, we had to find the secondary equation, which has to do with volume. And that's, again, up here on the right. The volume was given as 14 cubic centimeters. And so we get this equation here in terms of r and h. And we ended up solving for h in terms of r. And we got this here. And we plug that into the primary equation for h. And just to make that clear here, this h here became all of this. And when I plug that in, I just multiplied out the 2 pi r here. And we got this, and we simplified, right? We got this expression for a strictly as a function of r. I'll remind you again, pi is a constant. It's not a function of pi. Pi is not a variable. It's a number, right? Okay, so, all right. And I know I keep skipping step 4 here, but this is the result of step 3. A very important step, and again, a very long one, but a very important one. Step 4 is to find the domain. Right? So what's the domain of this function? Well, what could the radius be? Right? The radius is the radius of either the sphere or the cylinder. Can it be as small as I want? Can I make the radius 0? Well, if I make the radius 0, that shrinks the cylinder down to nothing. Right? And if there's no cylinder, there's no volume. And we can see that in the equation, right? R can't be 0 because we're dividing by r. So you can't divide by 0. Right? So r has to be positive. It has to be strictly bigger than 0. Not equal to 0 because, well, you know, then the area will be infinite, right? Or it won't make sense. You'll be dividing by 0, which is undefined. Okay, so the radius certainly has to be positive. Can it be as big as we want? Can we make the radius bigger and bigger? Sure, that would just mean h shrinks smaller and smaller. Okay, so I think there is an upper limit on the radius here. I just don't know if that's going to be clear. Well, let's suppose, all right, so here's our secondary equation. What happens if we allow h to approach 0? In other words, the height of the cylinder becomes smaller and smaller. It becomes like a pancake, right? Very short cylinder, the height shrinks to 0, and eventually we just get the two upper and lower spheres. So eventually it just becomes a sphere. So what happens there, if this whole thing is 0, I think we can solve for r then, right? I don't know if I can squeeze that in here, but can we solve this for r? Remember, if h is 0. Sure, that's not hard. Let's see, r cubed is going to be 14 times 3 over 4. So let's see, 14 over 4 is 7 over 2. And 7 times 3 is 21. So 21 over 2 pi, I think. Now, if that's r cubed, then the cube root of that is, well, r will just be the cube root of 21 over 2 pi. So I think that's the biggest radius here. The biggest radius is the cube root of 21 over 2 pi. I hope I got that right, but not exactly sure, right? Right, and that's assuming that h is 0. So h can't be 0. Actually, I don't know why h can't be 0. h could be 0, right? I suppose then you're saying that there's no cylinder. And in the problem, there's clearly a cylinder here. So I don't know. I guess it doesn't matter. If you want h to be 0, fine. But I think in the parameters of the problem, there is a cylinder, so h should be something bigger than 0. Okay, so that's the domain. Again, is that going to matter here? Probably not, because these are not equal. And if they're not equal, then, well, we know r can't be 0, but maybe this can be equal here. Let's say this can be equal to the cube root of 21 over 2 pi. So question mark, maybe that can be equal. Okay, so that will come up later. Okay, now what's next? Next is step 5. Oh, and I erased the steps here. Step 5, is, of course, is to finally maximize the function a of r. Or minimize. Sorry, we're minimizing it here. But it doesn't matter. Whether you maximize or minimize, it's the same procedure in step 5. Right, find the critical number. So take the derivative. And then set it equal to 0, right? So this will be what? This will be 8 pi r over 3 minus 28 over r squared. Again, the only critical numbers come from where this equals 0. Or you might say, well, wait a minute, what if r equals 0? Then the derivative will fail to exist. That's true enough, but I think we said earlier that if the radius is 0, there's no cylinder, there's no sphere, the volume would be 0, and that can't happen. So there's definitely no equal sign with the r equals 0. That cannot happen here. So no, the only critical numbers come from where the derivative equals 0, and you can solve this pretty easily, right? I mean, if you haven't done it already, go ahead and do it. Right, so cross multiply, and you get, let's see, 28 times 3. I want to say is 84, but don't hold me to that. 28 times 3, yeah, 84. And that's going to equal 8 pi r cubed. So divide by 8 pi, because we're solving for r. And so r cubed is going to equal 84 divided by, let's see, 4 is 21. So 21 over 2 pi. Is that right? Hang on, I just want to make sure. 84 divided by 4. Yeah, 21 over 2 pi, right? Yep, I'm a little surprised because we know where this is going now, right? R is just going to be the cube root of 21 over 2 pi. Well, doesn't that look familiar, right? That was the endpoint of the domain. And so as it turns out, this question mark here is a definitive yes. The radius can be this, this quantity here. Okay? Yeah, it turns out to be the endpoint of the interval. In this case, the right-hand endpoint. So there's definitely an equal sign here. Right? So yeah, the only critical number is the right-hand endpoint. There's no critical number between 0 and the cube root of 21 over 2 pi. Okay, so to answer the question, let's see. Find the radius. Oh, that's the answer. This is the radius, right? So there's the answer. This is the radius. It's exactly the cube root of 21 over 2 pi. For you engineers out there, you probably want an approximate answer, so go to your calculator. And I get about 1.5. Well, let's be a little more precise here. How about 3 decimal places? So 1.495. Yep. Oh, what are the units? Cubic centimeters, right? So radius is a distance. This is in centimeters here. Right. So very close to 1.5 centimeters, right? And I should have put centimeters after the exact answer too. But there you go. That answers the question. Or does it? Right? How do we know that it's a minimum surface area and not a maximum surface area? So again, we can use the second derivative test or the first derivative test. Either one's going to be pretty tricky here. Well, here's the derivative, right? Here's the first derivative. Can we take the second derivative of this? Yeah, no problem. Do we want to, or do we just want to use the first derivative test? Again, totally up to you. I'm going to use the second derivative test. I think taking the second derivative here should be pretty routine. 8 pi over 3, and then let's see, I think we get a plus 28 times 2, 56 over r cubed. Okay. So now we just plug in, well, this number, and you can plug in the approximate number, but I'm going to plug in the exact number. If you think I'm crazy, look, we know what r cubed is, right? R cubed is exactly 21 over 2 pi. So we get 8 pi over 3 plus 56 over 21, and then divided by 2 pi. So we get 2 pi in the numerator here. So what do we get? We get 8 over 3 times pi plus, this is a 21, right? Yeah. So 56 over 21 is 2 2/3, which is, I think, 8 over 3. Yeah, divide top and bottom by 7, right? So 8 over 3 times 2 pi. So times 2 here. The pi goes on the outside, right? So 16 plus 8 is 24 over 3. So I think that's just 8 pi. And 8 pi is certainly positive. So if the second derivative is positive, we know we're concave up, which happens at a minimum. So yes, we minimize the surface area. Okay. Oh, what is the minimum surface area? Take this number here, this r here, and plug it into the original equation for r, for the area, sorry. Again, maybe I'll do that up. Yeah, maybe I'll do that here. So 4/3 pi r squared This will not be nice. Obviously, you can just plug in the approximate answer in your calculator. That's probably the way to go. So maybe I'm, yeah, just being a little fastidious about this. So 4/3 pi, 4 pi over 3 times this thing squared, right? So 21 over 2 pi to the 2/3 power. And then plus 28 over r. So if you divide by r, you multiply by the reciprocal. So that's going to be 28 times 2 pi over 21 to the power 1/3. Right. Whatever that is, right? That gives you the minimum surface area. They did not ask for this. They just asked for the radius that gives you the minimum surface area. Okay. But, now we can find it. Or at least approximate it to, say, 3 decimal places. But there you go, right? So to answer the question, find the radius of the cylinder that produces the minimum surface area. And that's this answer right here. It's very close to 1.5 centimeters. In fact, they didn't say how far to approximate or how far to round. So if you said 1.5 centimeters, probably close enough. 1.5, right? But yeah, more precisely 1.495 centimeters. Right. So what's really going on here, right? The idea here is that when r is this number, right, h was 0. So what is the minimum surface area? The minimum surface area occurs when you just have a sphere. If you try to stick in a cylinder here, and I know I'm running out of space, but even if you stick in a very thin cylinder here, all you're doing is increasing the surface area. You're making the surface area bigger while keeping the same volume, of course. So yeah, to get the smallest surface area, you don't want any cylinder at all. Which then begs the question, why does the problem say there has to be a right circular cylinder? Well, maybe if you read it carefully enough, there doesn't have to be one, but there is in this particular case. So, yeah, so in this particular case, the right circular cylinder essentially disappears. When you increase r, you decrease h. Eventually, h does go to 0, right? So this is effectively the limit, right, as h goes to 0. As h goes to 0. And then this is the results. Just a single sphere. Actually, it's a ball because it's a solid, right? Right. And in fact, if you plug in this r into the, well, let's do it. Let's just double check. If you plug in, right, r is equal to the cube root of 2 pi over 21. Yep, no, 21 over 2 pi, sorry. I have it right here. If you plug that into the formula for the volume of a sphere, well, you better get 14, because that would be the volume then. So is that what we get? Right. So 4 pi, so this is just a check, you don't have to do this. 4 pi over 3. And then, well, good thing we need r cubed here. So r cubed is just going to be 21 over 2 pi. Okay, and what do we have? Well, the pi's cancel, right? Pi over pi is 1. And 21 over 3 is 7. So we get 4 times 7 over 2. 2 times 7 is 14. So that's pretty convincing. 14 cubic centimeters. That is the volume of a sphere. Okay, so the effect of increasing h obviously decreases the radius, but its other effect is to increase the surface area. So I hope that does it. Again, not an easy problem, right? This is definitely a harder problem. which is why I'm doing it. In this second video, this is more of an optional challenge problem here. But it's a good one, and hopefully you got it, or at least you came close. You had the right idea. But for now, we'll move on to one last one as a super challenge. Okay, so this is definitely the last one we're going to do, and it's probably the hardest one, right? It is also in the homework. I don't know if I asked a specific question in the homework or some similar one. I think in WebAssign it might be similar. But yes, this is in the homework. So again, I would encourage you to try this on your own. And if you get stuck, you probably will, because like I say, this is not an easy one. If you can get this, I would, you're solid A student, should be able to get this. But if you can't do it, well, you could probably still get an A in the class, because this is, A+ material here. Not an easy one. All right, so now I noticed in the book they draw the picture for you and they label everything, but I would encourage you not even to look at that. Try to draw your own picture here, just based on the description. Because that's kind of important. Again, and like the last problem we did not have a picture. We had to draw the picture of the cylinder and the sphere and all that. So I would just draw the picture and see if this makes sense, right? So we have a man in a boat 2 miles from the nearest point on the coast. Okay, well, here's the coast. We're assuming it's a straight line. I know, the shore isn't always straight, but here it is, right? And then here's the ocean or the water, right? And then over here is the land, obviously. Right. Okay. So here's the boat, let's say right about here. So this is point P, and we know it's 2 miles from shore. So the distance going directly to the shore here would be 2 miles. But he's traveling to a point Q located 3 miles down the coast. So here we have to go 1, 2, 3 miles. This is 3 miles down the coast, right? And then 1 mile going inland, like this. Okay, so this is your point Q, 1 mile from shore, but on land, right? And 3 miles from the point directly south of point P. Okay, so that's the picture here, right? And so what do we want? We want to travel from point P to point Q, right? And at 2 different speeds though, right? The rowing speed is 2 miles per hour. So you can row 2 miles per hour on water, but on land, your speed is, so land speed is 4 miles per hour. So keep that in mind, 2 different speeds. Toward what point on the coast should he row in order to reach the point Q in the least time? The least time, right? So what are we trying to do here? We're trying to minimize our total time. Minimize the time. Okay. So, as a first guess, you might say, well, look, the shortest distance between the 2 points is just a straight line. So maybe I should row to this point on the shore. And you can tell that's 2 miles from this point and 1 mile from this point. So that's a reasonable guess. It's a reasonable guess, right? That might be the quickest way to get there. But we don't know that for sure. In fact, if it takes, look, our rowing speed is slower. So that means we're going to spend more time in the water, right? So if we're spending more time in the water, we're going very slow here. Sure, once we get to this point, we can walk much faster to point Q, right? But you can imagine the worst case scenario is we row way over here, going very slowly, and then we work maybe a little bit backwards, we can walk faster. So maybe we should row all the way to this point and then just walk directly to point Q, directly south, right? But we're spending an awful lot of time in the water here. I mean, of course, we're walking pretty quickly here, but that's a short distance anyway, right? On the other hand, if we row directly to the shore this way, that might take a while, but then we can walk fairly quickly to point Q, and maybe that's quicker. But again, we don't know, right? That's the whole question. So the question is, where on the shore should we land? Maybe right here. So maybe some combination of those, right? Somewhere in the middle, we row to this point here, and then we walk the rest of the way here. Okay, so we already have this point P, this point Q. Let's call this point S. S for shore, because it's right on the shore. That's okay, right? So that's the point we want to land at, and we want to minimize the total time to go from P to S, and then from S to Q. Okay. So how do we calculate that time? So what is time? Right. Well, right. Notice these are speeds here, and they didn't tell us, are these instantaneous speeds or average speeds? It doesn't really say, does it? So why don't we just assume that this is our average speed, which means it's a constant speed, right? Let's suppose that our speed is constant, both on water and on land, that these are constant speeds. Okay, so in that case, right, your speed is just distance divided by time, right? Your average speed, right? Which means your time then is distance divided by speed. Distance divided by speed is time. So that's the formula I think we should use here. For time, we'll just take the distance we travel divided by the speed that we travel. Okay? All right. So what's the distance we travel? Well, notice there's two distances, right? There's the distance from point P to point S. And what is that distance? Well, right, it's just the distance formula between these 2 points. What are the coordinates of these points? Well, I don't know. That depends on, what we label as our origin. Why don't we call this point right here 0, 0? Right? So this is x equals 0. And this distance, we might as well call that x, right? And that's what they do in the book. They call that distance x. Right. What about this distance? Well, if the total distance from here to here is 3 miles, right? In fact, let me get rid of the 3 miles here, right? Then this distance has to be 3 minus x, so that the total distance from here to here, x plus 3 minus x, is just 3 miles. Make sense? Okay, good. So the question remains, what's the distance from P to S, this yellow distance here? Okay, so I hope this is not hard. In fact, let's just draw the triangle here. Right, so this is x. This distance is 2. That's a constant, 2 miles. So this distance here, I don't want to call it d. How about, I'm running out of letters though. How about a? So, well, we could use c like in the Pythagorean theorem, right? So c squared is just x squared plus 2 squared. Or c is just the square root of x squared plus 4. Okay, so that's the distance, right? From P to S, the square root of x squared plus 4. Okay, but that's only the distance you're traveling through water. What about the distance on land from S to Q? What is that distance? Right, so another triangle, this one here. Maybe I should draw that down here. Okay, so this we said was 3 minus x. This distance here was 1 mile, right? So 1 mile. So what's the hypotenuse? Well, if I use C here, how about B? Or how about A? I don't know. I'm running out of letters. A is good. Right, so A squared equals 1 squared plus 3 minus x squared. And if you multiply that out, I mean, you don't have to multiply it out, though. You can just let A be the square root of 1 plus 3 minus x squared. But let's do it, right? So this is 1 plus 9 minus 6x plus x squared, which is the square root of x squared minus 6x plus 10. And let me just copy that down here. There we go. There's the two distances from P to S and then from S to Q. Right. So what's the total distance? Well, then just add them up, right? Take one plus the other. But we're not interested in the total distance. We're interested in the total time. Okay. So how do we calculate the time to go from P to S? So I guess I'll call that capital T for time. And we're going from P to S. So time is the distance. Well, this is the distance. It's the square root of x squared plus 4 divided by the time. Divided by the speed. How fast were we going from P to S? P to S is in the water, and that's the rowing speed. That's 2 miles per hour. So divide by 2, right? Because that's the speed. Okay, so that's the time it takes to go from P to S. How about the time it takes to go from S to Q? So that's on land. Well, again, distance, we know the distance is still S to Q, so that's going to be the square root of x squared minus 6x plus 10. And then all divided by the speed. The land speed, the speed for walking is 4 miles per hour, so we'll divide by 4. And that's the time walking on land. So your total time, assuming we don't, take a break when we come to shore, that we get to shore, we get off the boat, and we immediately keep going. The total time then, so total time, right, is just the sum of the two times. Sorry, T here, right? So when we add these up, we get T now. And notice that this is going to be a function of x, because there's only x in the expression here. Right. And there's our function. Right? This is our primary equation, right? This is the function we want to, well, minimize, right? The least time is the minimum time. So, yep, there's no secondary equation here. If there was, it might be, the Pythagorean theorem or figuring out the time in terms of the distance and the speed, but, right, it's already a function of one variable. So, small favors here. Our step 3 is done. We don't have to eliminate any variables here or make a substitution. Right. So, what is the domain of this function? What's x allowed to be? Well, what is x, right? X is the distance in this triangle here, right? This triangle here. I guess it could be 0, right? If you go straight from this point to this point. Or it could be 3 if you go from this point to this point. It's pretty clear, though, that what you don't want to do, and I kind of mentioned this earlier, you don't want to row all the way from this point to this point and then backtrack to this point. That'll clearly take you a lot longer than it would just to go from here to here. Right? Not only is it a bigger time, it's clearly a much bigger distance. Right? So, yeah, I don't think we want x to be bigger than 3 or less than 0. So the domain of this function, x should be between 0 and 3. And I think we can allow it to be 0 and 3. You never know. We might want to go directly to shore here. So, yep. So the domain in interval notation is 0 to 3, including 0 or 3. I think those are possibilities. I would be very shocked if x is bigger than 3 or less than 0, because you're just making it a bigger distance, and you're, well, if it's a bigger distance, it's a longer time. Make sense? Okay, so everyone okay so far? This is the total time to go from point P to point S, and then from point S to point Q. So, how do we minimize this time? Usual way, critical numbers, right? Take the derivative and set it equal to 0, right? Or determine where the derivative does not exist. Either way. Well, look, this is a sum rule, so I think we just take the derivative of each term. I don't think we need the product rule here, because this is a sum. So that might make it a little bit easier. Before we do that, though, right, because we can see what's going to happen here. We're going to be taking the derivative of these square roots. So before we take the derivative, how about if we write it this way, right? 1/2 times x squared plus 4 to the exponent of 1/2 plus 1/4 times x squared minus 6x plus 10. Again, because it's the square root, it's to the power 1/2. I think it'll be easier to take the derivative in this form than in the original form, square root form. Okay, now we can take the derivative. So t prime of x, or dt over dx, either way. So 1/2 times 1/2 is 1/4 times x squared plus 4 to the negative 1/2. Right? And then don't forget the chain rule. The derivative of x squared plus 4 is 2x plus 0. Okay. And then for the second term here, 1/2 times 1/4 is 1/8 times x squared minus 6x plus 10, again to the power negative 1/2, and then the derivative of what's inside the parentheses, 2x minus 6. And I'm running into this calculation here. Don't get confused with that. So there's our derivative. Is there any way to simplify it? Well, let's see. So this is 2 over 4, which is x over 2, times the square root of x squared plus 4. Yep, I'm going back to radical form. You'll see why in a second. And then 2x minus 6 divided by 8. Well, 2x minus 6 is 2 times x minus 3. And when you divide by 8, you get 1 over 4. Times the square root of x squared minus 6x plus 10. And then in the numerator, we still have the x minus 3. Right? We cancel the 2 with the 8 here. So I think that's it, right? I think that's the derivative. You know, clearly we could rationalize the denominator, but I wouldn't bother doing that. So if that's the derivative, what are we looking for? The critical numbers? The critical numbers are where this equals 0. And let's assume that the derivative exists. Clearly this is going to be positive. I'm almost sure that if you use the b squared minus 4ac, that this is also going to be positive. So the only critical numbers also come from where this equals 0. And I would almost be surprised if there's any problems in this section where you get critical numbers where the derivative does not exist. It could happen. It's not. It is a possibility. You always have to make sure you check for that. But in most of these practical problems, these optimization problems, that's not going to happen, right? So we have to solve this for x. How do we solve this for x? Yeah, not easily, right? We can try to get a common denominator here. But I think instead of doing that, I'm just going to subtract one side from the other. Okay, so on the left side, let's leave this as x over 2 square root of x squared plus 4. On the right side, we get a negative x minus 3 all over the same denominator, 4 times the square root of x squared minus 6x plus 10. Right. Why would I do that? Well, we have a fraction on both sides, right? So we can just cross multiply. Now before I do that, I'm going to put the negative up here, right, and distribute the negative sign so we get 3 minus x. I mean, you don't have to do that, but again, I think that will make everything easier later. Right, so that's a 4. Yep, so the numerator is 3 minus x, the denominator is the same thing again. Minus 6x plus 10, yeah. Right, and now just cross multiply, right? Multiply both sides by the least common denominator. And when you do that, what do we get? 4x times the square root of x squared minus 6x plus 10 equals, let's see, 2 times 3 minus x times the square root of x squared plus 4. Okay. Now, does that make this any easier? Doesn't look like it, right? This is not a simple equation to solve. In fact, I would say this is pretty tough, right? What can we do? We can square both sides. That'll get rid of the square roots. Oh, before we do that, why don't we isolate the square root? I'm going to divide both sides by the square root of x squared plus 4. So we get the square root on the left side, not the right side. And while we're at it, why don't we divide both sides by 4x? Right, so these cancel, and these cancel. And now the left side is just one big square root. Yeah, I mean, I don't know if this makes it any easier or not, but that's a 4. And then the right side is what? It's 2 over 4 is 1 over 2, so 3 minus x over 2x. Okay. Right. Again, we're finding the critical numbers, right? We took the derivative, we set it equal to 0, and now we're solving for x. So now I think this is a good time to square both sides, get rid of that square root. So the left side is just this. The right side, well, now we have to expand this out, right? This is going to be x squared minus 6x plus 9 divided by 4x squared, right? You got to square the top and the bottom here, right? So again, doesn't look like we're making much progress here, does it? Except we got rid of the pesky square roots. No more square roots, right? And now what? Well, now we have a fraction on both sides, so we can cross multiply again. So it's just back and forth, algebra, back and forth here, right? So 4x squared times x squared minus 6x plus 10. And that's going to equal, well, x squared plus 4 times x squared minus 6x plus 9. This does not look fun. But it's all just going to be a polynomial now, right? So multiply everything out. You're going to get 4x to the 4th minus 24x to the 3 plus 40x squared. And on the right side, well, you got to distribute, right? So this will be x to the 4th minus 6x cubed plus 9x squared. And then when you multiply by 4, you get 4x squared minus 24x plus 36. This funny thing is a 4x squared, right? Okay, having fun yet? So more algebra, just bring everything over to the left side. So 4x to the 4th, we got to keep track of this, right? So 4x to the 4th minus x to the 4th is 3x to the 4th. Then what? Then we have negative 24x cubed plus 6x cubed. That's the only cubed term, right? So I think that's going to give us, let's see, negative 24 plus 6 is negative 18, x cubed. Right? And then we have, let's see, the x squared terms. We have 40x squared on the left. And this is, oh, we didn't combine these, but this is 13x squared on the right. So 40 minus 13, 26, right? No, sorry, 27. 40 minus 13, right? 27x cubed. X squared. Boy, I'm getting sloppy here. I hope this is right? Now what? Add the 24x to both sides, and then subtract the 36 from both sides. And there we go. Now we just have to solve this fourth degree polynomial equation in x. This is not obvious, right? It's not a quadratic equation, so there's no quadratic formula. There's a quartic formula, but I don't know it. So I think this is a good time to bring up your calculator and just do this on your calculator, because trying to do this by hand will be not so easy. Okay, so give me a second. I'll bring up the calculator and I will use it to solve it. But essentially, just graph the function and look for the x-intercepts, right? Where does it cross the x-axis? Okay, so, well, let's see. I graphed it, and it looks something like this. So here's 1, -1, -2. Let's see. Hang on. Yeah, so something like this. Right. So the x-intercept looks like it's 1. So it looks like x equals 1. And so let's check. If I take 3 minus 18 plus 27, so 3 minus 18 is -15, plus 27 is 12, plus 24 is 36, minus 36 is 0. Yeah, it works out. So x equals 1. Well, I don't know. Maybe we could have guessed that, but yeah, that's what it is. It's just that simple. Now, there is another answer here. This one is approximately -1.17. No, sorry, -1.1117. Yeah, -1.1117. Right, if you approximate. So what's wrong with that? Well, remember the domain. X can't be negative here. It's got to be bigger than 0 and less than 3. So they're clearly less than 3, but this is not less than 0, not bigger than 0. So I think we can safely discard the negative answer as just not physical. You know, doesn't make sense for the problem. Okay, you know, I mean, look, it's a critical number, right? Maybe it gives you the maximum time instead of the minimum. So I would count on the x equals 1. Right? Okay, so what does that mean? That means that when x is 1, and that looks about right here, right? That's 1, that's 2, that should give us the minimum time. Right? So we should row to a point, right? Well, if we call this point here 0, 1 mile away from the point directly across from point P. Does that make sense? So, yeah. So if 0, or maybe the point O, is directly across from point P, which is where we started, right? So P has coordinates 0, 2, O has coordinates 0, 0, then we're rowing to get to the shore, right, to reach point, oh, I called it S, so 1 mile away from 0, 0. So 1 mile from point O. Sorry. From point O, 0, 0. Again, go back to the, sorry, 0. Go back to the picture that I drew right up here, right? Or maybe just let me make a new picture. So, yeah, here's the shoreline, right? Here's the point P. There's where we're starting at 0, 2. Here's the point directly across from the shore, 0, 0, what I call point O, right? And we're, let's see, 1, 2, 3 miles away, and then 1 mile inland. This is our point Q. If we want to get from point P to point Q the fastest, we don't want to go directly there. We want to row to this point 1 mile from point O. So row that distance first through water. And then when you reach the shore, get out of the boat and walk the rest of the way twice as fast. And that'll get you there in the quickest time. Okay? So that's it. That answers the question. So 1 mile away from, not point P, right? Effectively, it's, I think, the square root of 5 miles away. So the distance you're rowing, right, if this is 1 plus 4, square root of 5 miles. Right? And then the distance from point S to point Q is, let's see, 1 plus, this is 2 squared, which is, wait, that can't be right. That's also square root of 5. Yeah, I think that's right, because this is 2 miles. All right, so my picture's a little wrong here. But yes, basically the distance you're traveling is 2 square root of 5 miles, exactly. But the question wasn't the distance. The question had to do with the minimum time. What is the minimum time? Well, go back to the equation for time, which is up here, right? So this equation up here, what do? We plug in our critical number, x equals 1, and what do we get? So I'm running out of space. Can I squeeze that in here? So this is going to be the minimum time. Plug in x equals 1, and we get, square root of 5 again. That's the distance divided by the speed, so that's the time in minutes? Hours. Right, miles per hour. Right. And then plus, let's see, so square root of 1 minus 6, negative 5, plus 10 is positive 5, so square root of 5. But this is over 4. Okay, so this will be 3 times the square root of 5 over 4 hours. So that's the shortest time we can get there. And just to approximate that, square root of 5 times 3 over 4 is about 1.677, 1.677 hours. So, very roughly 1 2/3 hours, right? So if I'm approximating this with 2/3, 2/3 of an hour is 40 minutes. So 1 hour and 40 minutes. Right. Is that, I think that's right? 20 minutes, yeah, that's 1/3 of an hour, so roughly 2/3. Again, this is approximate, this is not exact, right? Even this is approximate. This is the exact amount of time it'll take. Because this is, 2 over 4 plus 1 over 4. 3 square root of 5 over 4, so again, that's it, right? If you're not convinced by this, what you can always do is pick a different x. Like, let's say maybe you think x should be 1.2 miles. Plug that in the same function, and you'll see you should get a time that's a little bit bigger, right? And maybe it's not much bigger. Maybe it's 1 hour and, 43 minutes. But it's still longer, right? It still takes longer, and we want to minimize the time. So this is the minimum time right here, minimum time. Spell it out. Right. And that's probably what I would ask you on a test. What is that minimum time? Their question was a little bit awkward. Right. What is the minimum time? Because that's a numerical answer. What point should they row to? Point S, which is 1 mile away from the shore. So that's this answer here. In words, right? Row to reach point S, 1 mile from point O, which is the origin, which is, in the picture here. So, yeah. Anyways, that's this problem. I warned you, right? This was not easy, and a lot of algebra here. And in the end, we got this equation right here. This equation turned out to have a very nice solution, but this did not look one like I could solve just by doing synthetic division or something. I just used my calculator and got two real solutions. The negative one we can ignore, and the positive one was 1, which is, again, a nice number. But it didn't have to be that way, right? In other problems, your x might be, 1.72 or something. It might be approximate. So it turned out to be a nice answer here, but a lot of trouble to get it. So just be aware of that some problems you might have to resort to using a calculator or computer to solve a very complicated equation. And while this looks complicated, it's probably less complicated than trying to solve this by hand, right? So most of this was just algebra to simplify it to a polynomial equation, which works much better in your calculator than does, say, this equation here. You could probably do both, but this one looks nicer, that's all. I think that's it. I think we better end it here. Is this going to be on a test? Obviously, very unlikely. This would be sort of the challenge of all challenges, extra credit type question, which I'm not likely to put on a test, right? I think all the other ones we did were either reasonably, kind of a medium problem, or maybe a little bit of a challenge, like the last one with the spheres and the cylinder. But most of the problems in the first video, I think, are reasonable. The two problems we did in this video are either very challenging or you can almost say excruciatingly difficult. But look, not all problems are going to be easy. You got to get used to this, right? If you want to be an engineer or a scientist or anything, you got to get used to hard problems. And, in the grand scheme of things, this was not a hard problem. This is probably one of the easier ones that can be done, and we get a nice exact answer. So just realize that, they're not all going to be easy, nice problems like the first one we did in the previous video. Yeah, as far as tests go, I would not worry about these types of problems. If you can do this, if you got the right answer, that's excellent. When I was taking calculus, I might not have been able to do this on the first run either. This might have taken me at least a few hours, if not a few days, to figure out. So it just takes a lot of practice. I've done this a lot. All right, I'll end it there. Good luck and enjoy the other ones in the homework. There's plenty of other examples involving either distances, find the shortest distance, or maximize your volume, or whatever. So have fun.